Hi, Thomas.
Hi, Peter.
Welcome to my podcast on daily life metallurgy, or in Danish, Hverdags Metallurgy. I know you know some Danish, but you would prefer to do it in English this time.
Yeah,
Maybe
I think that's better. Maybe in a couple of years, my Danish will be better.
Yeah, well, I'll come back to you later. Thomas, you're working with spray forming, as can see on the picture behind you, and spray forming was in fact my first child within metallurgy. My first job was at a spray forming plant, making high alloy tool steel, and that's why I'm reaching out to you now, because I want to learn what is going on with my first child. Are you taking care of it, and are you further developing it? But first, will you give an introduction to yourself, your educational background, your name, and what you're doing today?
Yeah, sure. First, yeah, thanks for inviting me to this podcast series. I feel very honored. Also, yeah, I haven't been that long in Denmark, and then it's nice to be able to participate in this podcast series. So yeah, my name is Thomas Dahmen. I am from Germany, and yeah, I took my education as a mechanical engineer in AISI H13 University, and yeah, and I would say I didn't have the typical metallurgy education as a metallurgist. So actually, my bachelor degree was about mechanical engineering and business administration. So that was like a kind of a two majors, but it was mostly focused on mechanical engineering. And then I continued that in my master's as well, and had external stays in China and in the US. And then slowly I got interested in metal 3D printing. That's actually something I specialized in. So I specialized in production engineering, and then further in 3D printing, or it's also called additive manufacturing. And then after that, I got started a PhD education at the Technical University of Denmark. And that was an industrial PhD project I had with MAN Energy Solutions, so the company that makes large two-stroke diesel engines. And yeah, I was my topic was to investigate how we can 3D print large components, or in general components for diesel engines. And then and from that, there was very much focus in the beginning in the process. So I compared different 3D printing processes, like laser powder bed fusion or binder jetting. Those are two different metal printing processes. And I also looked into this design, how to improve the design of fuel injectors. And then actually the last third of the project was very much about materials and about what kind of materials can we print, and what kind of structures do we get after printing, and how can we optimize the structures by tailoring the heat treatment. And that was really the first time where I sidetracked more and more towards metallurgy. And then after my PhD, I got offered a postdoc position at DTU again, but then that was in the materials section, where I then had something very much focused on material science with that project that brought me to spray forming. And yeah, I can probably talk more about that later.
yeah, and going from 3D print to spray forming, you could say a spray forming plant maybe is the biggest 3D printing plant in the world, because you are adding layer by layer, like you do in 3D printing. But in spray forming, we talk about typically 4 tons per hour. which is a bit faster than the most additive manufacturing technologies that are on the market.
Yeah.
But can you go a little deeper in explaining what is spray forming? How does it work, and why does it work?
Yeah, sure. So you're right. I also, because I come from a 3D printing background, basically, I also see it. We basically have the largest 3D printer, you could say, because we can print like those 80 kilograms per minute. And yeah, how a spray forming plant works is that we first liquefy the metal. So we melt down the metal, and we have an induction furnace in which we melt, and we aim to use 100% scrap steel, because we want to have a circular recycling process of our steel. And after melting it down, we pour it into a tundish, and from the tundish, it is atomized through 2 atomizers that are driven with inert gas, such as nitrogen. So until here, it's very similar to normal gas atomization. But then we have a special nozzle system. So the nozzles, they scan and can change the direction. And what you also see in my background, you see the 2 nozzles set up inside the spray chamber. And what happens is the liquefied steel is atomized into little droplets. And these droplets are then sprayed or deposited onto a turning build plate that collects all those particles, and there you have a solid steel building up layer by layer, and at the same time the build plate retracts while it spins, and that way we get a very homogeneous steel, because we have relatively high cooling rates. So this process is especially useful for highly alloyed steels where you don't want a lot of segregation.
Yeah. Can you also do it in other alloy systems?
Yeah, so our plant is mainly focused on iron alloys. We're focused mainly on tool steels, but in theory, I mean, there are some spray forming plants running on aluminum, and basically there's no limitation, I think. I mean, I know from literature that there were some plants also for nickel-based superalloys as well. So it's all about, controlling the purity and the oxygen content.
Yeah. And I also know Wieland in Switzerland had a plant working on copper alloys, where they added graphite to increase the hardness, but remain the high conductivity.
Yeah. So actually it opens up a lot of possibilities, not only for single alloys, but you can also use metal matrix composites, for example. I mean, we have 2 nozzles that spray the same material, but in theory you could even introduce in the tool steel world, you can introduce like hard phase particles like tungsten carbides or other hard phases, and that you could in theory introduce through another nozzle or silicon carbides to make metal matrix composite. So actually there are a lot of possibilities here.
So when you have your spray form product, is it ready for use, or what is next step on it?
Yeah, so it really depends on the application. So some alloys that we spray from, we can get a density above 99%, and that might be good enough for certain applications. But for critical applications, we recommend to hot forge the billet afterwards to further densify it. And then it also depends on your initial microstructure. If you want to, if you have a lot of primary carbides, for example, you want to break them up and distribute them even more finely. then you would have to include other post-processing steps, also to get it into the final shape that you like.
Could you give some insight in what is the difference if we take a standard tool steel alloy? I think the most common is a AISI D2. It's the working horse in the tool steel world. If you look at the carbides, how do they look on a traditional casted billet, and how does it look in a spray forming billet?
Yeah, so if we take that example, I mean that's a good example to showcase the benefits of spray forming for tool steels, and that is in normal casting of these tool steels, because they have a high carbon content and high, for example, in that, yeah, you have also high vanadium and relatively high chromium, so you form like a lot of these carbides, and the cooling rate is much lower, so the carbon diffuses to the grain boundaries where those carbides form, and then you get like brittle carbide networks around your grains, and these often also have sharp edges, and therefore you get a much more brittle material compared to in spray forming. And then usually after casting, those conventional steels, for example, if you hot roll or forge them, you get uneven wear properties. So you get layers where you have a lot of carbides, and then layers where there are no carbides, and then it doesn't wear evenly, and it's also more difficult to machine because your material is less homogeneous. And in spray forming in general, we get a much finer microstructure because of the high cooling rate. At the same time, we don't get the segregation, so we get finely dispersed carbides that also tend to be more spherical, which increases the, you could say the toughness, but also the hardness. So in general, you have this trade-off that the harder you make a material, the less tough it gets. But in spray forming, because we get a very fine structure with evenly dispersed carbides, we get a better trade-off and can achieve higher toughness and hardness compared to conventional cast materials.
And if we look into where can Mr. and Mrs. Denmark see any benefits of this? Where does it affect your daily life?
So first of all, yeah, maybe I would like to go one step back, why we actually do spray forming. Yeah. And so this technology was invented, I'm not sure, but like you probably know better than me, like in the 70s or 80s, and it struggled a little bit to be fully commercialized, and nowadays there are not many plants in the world, and that had a couple of reasons, but one reason was that in this technology, even though it gives a lot of those technological benefits, it has one shortcoming, that we don't have 100% efficiency in the yield of the material, because a lot of those particles that are atomized and sprayed onto the billet, they don't stick, and they fall down and end up as powder.
I think you can see it on the picture behind you. It's a little foggy.
Yeah, exactly. And that you can imagine are a lot of small particles that either have not hit the billet, or they were rejected from the billet because they were already too cold. And here we had this research project with the Technical University of Denmark to investigate what to do with those particles, because back in the days they were just remelted or stored away. Well, now we found out, and that was also my postdoc project, that these particles, powder particles, are very good for metal additive manufacturing, like binder jetting or laser powder fusion. And we've been using them to 3D print, and can see that the characteristics of this powder is on the same level or better than normal gas atomized powder. It's very spherical and with very low oxygen contents, and so it has a high flowability and everything you would expect from normal gas atomized powders. And this is why we're reviving the spray forming technology right now, because now we can get a much higher resource efficiency because we can use the billet and the powder at the same time. And we're also a little bit reinterpreting the spray forming technology as a recycling technology, because sustainability and circular economy is getting more and more important. And we have customers that are, it is important for them that they can reduce the CO2 footprint in their value chain. And what we do is we take the scrap from our customers and we basically upgrade it through the spray forming process. So we give it better properties, return it to the customer, and at the same time they can also use the powder for 3D printing.
So it's a buyback system.
Yeah, and in this way we are collaborating with RWTH Aachen University, but also the University of Southern Denmark to do life cycle assessments of this. And we could see that we can reduce the CO2 impact for these high-alloyed steels by over 80%.
Wow.
Through this. Yeah. Because also right now in Denmark, we're trying to build like local ecosystems for these steel recycling process. And in Denmark, over 99% of the steel is exported. So there's no real recycling industry. And that also adds up. It's not only the transport, and every time you throw away tool steels are ferritic, and or at least they're magnetic, and they're often then mixed with cheaper steels that are ferritic, but you have a lot of alloying elements in your tool steels, and these get diluted. And when they get diluted and you make new tool steel, you have to mine the elements and put them in as primary resources again. Yeah. And that is one reason. The other reason is also that in spray forming, we can, as a recycling process, we can allow a little bit higher impurities than in normal casting, because we finally disperse our elements in the steel. And that's why we get a relatively cleaner steel. And the third, maybe most important reason is that we get a very high quality steel without using classical casting techniques. So for example, when we make a high quality tool steel, usually you would either need to have electroslag remelting process to get a steel with very low impurities, or an evolution from there was a powder metallurgical steel, where you first atomize powder and then later you compact the powder together and use hot isostatic pressing to make a new material. And that material is, you could say, spray forming is quality bias between the casted normal casting and powder metallurgical steel. But spray form material is much more resource efficient because we don't have to make the powder first to compact it again. So we have a much shorter process chain, which is more energy efficient, and we use an induction furnace that can that we power with 100% renewable energies. And so coming back to your question about the everyday life, it is that 80% actually of the CO2 emissions are caused to metal production, either in mining or processing. And so that's a very, very big field. And we want to reduce the impact of steel, and that of course impacts every one of us in everyday life. That is one side of the story, the sustainability aspect. And yeah, the other side is, of course, when we talk about tool steels, how do they impact your everyday life? I mean, if you're listening to this podcast right now and you're sitting on a chair, or you're driving in your car, or you're running, you are in touch with materials and products that have been processed through tool steel. So you can imagine that if you take your chair or a table and it's made out of wood, it has been cut by a tool steel. Or if you're running with your shoes, it has been formed by also some forming tool steels. And maybe the easiest example is if you go to your kitchen and you have the knives. That is actually tool steel that you have at your home. It's typically a martensitic stainless tool steel. And through our process, because we get a much finer carbide distribution, we can increase the lifetime of these products. And we had some case studies with customers that could increase 3 to 5 times the lifetime of the tools before they had to renew them. Yeah, but that's also very application and material specific.
But it could make it is one of the reasons why we have products today that everybody can afford.
Yeah, exactly. Because if you think about traditional production tool steels, or if you think about plastic parts that need an injection mold, and these molds are quite expensive, and you need at least 10 to 50,000 shots to make it paying itself off. But then you can increase the lifetime of your tool by let's say to 100,000, and then in the end you pay less per part in your production, and that enables us to have certain products at home.
So next one, what is the future? Where are you leading us with your spray forming technology, Thomas?
Yeah, so right now we're kind of ramping up the production, and we're basically restarting an old plant. So we see ourselves as a startup, and right now we have to get enough showcases, demonstrators, and pilot customers to fully integrate this system into the steel recycling ecosystem. And that has a lot of challenges, of course, because I came from the world of metal 3D printing, and then when I started, if we look, for example, at laser powder bed fusion, there are like 1,000 process parameters. How to control the process is very complex. And back then I thought like that is special to 3D printing technologies. But I think most manufacturing processes have a lot of parameters, and we are also busy with optimizing the parameters also in spray forming. So we are still trying to also increase the quality and make the process more repeatable, and that is one of the bigger challenges, because when this technology was invented, end of the 20th century, they didn't have all the possibilities we had today with putting sensors into all different places and monitor everything and have in situ process control. And we're trying to implement all these kind of more industry 4.0 possibilities also into the plant. That is one thing that we are working on. But also, right now we're focusing a lot on just spray forming steels that are already there in the alloy composition. And I think in the future it would be good to develop our own alloys that can fully harness all the benefits from this technology.
Yeah.
So yeah, I mean I have many ideas what to do.
Yeah.
Yeah. But I think it's step by step.
Yeah. So the last question I have for you is now you told you came from a non-metallurgical or more a mechanical background. So what has been the most amazing metallurgical insight you have got within the world of spray forming?
Oh, that's a good question. Yeah, I mean, basically with my background, I had material science in my bachelor's, and then I didn't use it until my PhD. And then I also realized that in my bachelor's I didn't understand anything. Like because it was so abstract, and there was no connection to an everyday problem. And for example, when I started working with a fuel injector, suddenly I had to choose a material to which one to print in, and then you start reading up again about what are the benefits of which microstructure and what features. And so I really think once you connect something to an end application, you start really to understand, and also you start to memorize and remember that, because then it becomes more important. And then spray forming, I mean, we're spray forming steel for injection molds, or for knife steels, and then you have to ask yourself what makes a good injection mold or a good knife steel, and then you have to link it all the way back to when you go backwards. Then the steel has been machined, it has been heat treated before it has been casted, and you can basically link then when you're controlling the manufacturing process, which parameter causes what in your final application, and that's like a big puzzle, and I think that's very exciting, because you kind of discover those relationships, and then you need to understand them and correlate them, and I find that exciting.
Yeah, I fully understand. I have been on the same path many years ago, so I know you're struggling as well.
Yeah, there are a lot of relations to uncover.
Yeah. Thank you very much, Thomas, for sharing. I really enjoyed it, and I am personally so happy to see spray forming getting a revival. It's like the clothes. Now we are back in the 19s in what is modern to wear. Maybe also spray forming is becoming modern again to work with.
It seems like, as long as we develop it further. Yeah.
So thank you again, and I will come back to you in a few years, and we'll make a new one, but in Danish.
Okay. Yeah. Klar til det. Hopefully, let's see. I don't want to promise too much, but let's see.
I'll keep you up. Tusind tak.
Ja, i lige måde.